Is there always a clever shortcut for every problem where we can efficiently recognize a correct answer? And I think it's now recognized as one of the central unsolved problems in all of mathematics.
Scott Aaronson is a professor of theoretical computer science at UT Austin, particularly known for his work on quantum computing and complexity theory. Today we talk about free will, we talk about consciousness, complexity classes, superdeterminism, and even quantum computing. That last one in particular, we talk about what quantum supremacy actually means, rather than how it's promulgated by people like Michio Kaku and other popularizers of science. Scott explores and teaches these ideas with extreme simplicity, as well as joy, which is a rare combination. Welcome to this channel. My name's Kurt Jaimungal, and for those of you who are unfamiliar, this is Theories of Everything, where we delve into the topics of mathematics, physics, artificial intelligence, and consciousness with depth and rigor. This commitment stems from a recognition that popular science articles often peddle superficial falsehoods, leaving a discerning audience, like yourself, yearning for technical accuracy and substantive discourse. In other words, the audience of TOE is the audience that's willing to invest the extra time to understand the nature of reality and not be stuck in the mysticism that characterizes, say, Neil deGrasse Tyson, explaining that, whoa, quantum mechanics is both a wave and a particle. Cool, bro. Like, what does that mean? In order to understand how that's misleading, one needs to know what a complex linear combination is, and so we'd rather explain that than broadcast that a particle is both up and down at the same time. Enjoy this podcast with Scott Aaronson. Welcome, Professor. It's an honor to speak with you. I've been following you for a few years.
Thanks. Great to be here.
I mean that in a non-creepy way. What got you interested in computational complexity?
Well, I got into computer science as an adolescent because I wanted to create my own video games, mostly. And so I learned, what I could about programming, and really it was a revelation to find out that engineering, a video game, just reduces to, writing these lines of code. That was not what I had expected. I like to say that for me, it was like learning where babies come from. Like, why didn't I find that out before? And as I learned more about it, I realized that while I liked programming, I was really not any good at software engineering. At making my code work with other people's code, getting it done by a deadline, documenting it. And, if I had any comparative advantage, then it was probably, on the more theoretical side, right? Of, thinking about what kinds of programs could be written, couldn't be written at all, and I kept wondering about that. I mean, when I first saw Apple Basic, and then GW Basic and Q Basic, and these ancient languages, I figured, okay, to make a really sophisticated program, clearly you would need a more powerful language. Right, and it was a second revelation to me that no, you just very rapidly hit this ceiling of Turing universality, right? Where just a very simple programming language becomes capable, in principle, of expressing anything that any programming language could express. Right, and so then you could say one of the biggest remaining questions is about efficiency, right? Is about which among all of the problems that computers can solve, which ones can they solve in a reasonable amount of time, right, or a reasonable amount of memory? And so when I was 15 or 16, I would have learned what is the P versus NP problem. And that problem is just so stunning, that humans could ask something, so basic and yet, so concrete, that has a definite answer one way or the other. And I had fantasies for a few months that all of these experts must have gotten stuck in a rut, and I'll come in as a 15-year-old and with no preconceptions, and I'll polish this problem off. I think it was good to have that experience.
Yeah.
Once in my life, once was enough to get disabused of that. And then at some point, I learned about quantum computing, which we can talk about more. But that actually changes the rules of computational complexity, based on our best current theory of physics, right? And that was then irresistible to understand, because somehow these very basic questions in physics and in computer science were merging with each other, right? And it was all a story about computational complexity. I mean, if you don't care about complexity, then there's basically no reason to build a quantum computer, right? And anything it can do can be simulated by a classical computer, albeit exponentially slower. Okay, so you need complexity theory to even pose the questions about what are quantum computers good for. And but this was a field where there was a lot of low hanging fruit, in the late 1990s when I started really getting into it. And I was also extremely interested in AI. I thought maybe I would do that. But again, there was the difficulty that AI so often boils down to, in practice, to software engineering, which I wasn't so good at. Now, it was when so I was an undergrad at Cornell. When I applied for grad school, I got into where I really wanted to go, which was UC Berkeley. But it was the AI people who recruited me there, not the theory people. But I sort of, secretly, I guess, wanted to do quantum complexity theory. So after a year of doing AI, I switched. And so and then I ended up computational complexity and quantum computing ended up being interesting enough that I've spent more than 20 years of my life on them now. And only now, finally, in the last couple of years, I'm circling back to AI with the stuff that I'm doing for OpenAI.
Yeah, I'd love to speak with you about your work at OpenAI. Now, first, is computational complexity, algorithmic complexity, and quantum complexity distinct?
Well, I would say that computational complexity is the whole field that studies sort of the inherent computational resources that are needed to solve problems, right? And that includes time, memory. It could include energy, randomness, parallelism, and quantum computing is a part of that. Right, you could say quantumness is another computational resource that you can throw into the mix, and then see how it changes things. So yeah, but it is the field that studies sort of the inherent capabilities and limitations of algorithms. Sometimes people who are only interested in just solving a practical problem with the best algorithm that they can find for that problem, they might not call themselves complexity theorists, right? They might just be algorithms people. But as soon as you start asking the question, what is the best algorithm for this task, in terms of the scaling of resources as the input gets larger and larger, how do I know that it's the best algorithm, right? What else would it imply if there were a faster algorithm? Okay, as soon as you start asking things like that, then you're doing complexity theory.
It sounds like it's easy to show that something is a more efficient algorithm than another, but to show that something is the best, how do you go about doing that?
Yes, well, good question. The field has been struggling with that for half a century. In order to give a faster, in order to show that there is a faster algorithm to solve a given problem, typically the way you do it is you just give that algorithm. You give it, and that could already be very non-trivial because you have to analyze the algorithm. You have to prove that it works, and you have to prove that it actually terminates after this reasonable amount of time. Okay, so that can already be non-trivial. Okay, but now if you ask, is this the best algorithm? How do we know it's the best? Okay, now you're trying to prove a negative, right? And that is inherently a vastly harder undertaking. And in some sense, the main reason why we view it as a goal to strive for at all is that computer science was sort of born with knowledge about its own limitations, right? When Alan Turing introduced the Turing machine, which is sort of the mathematical model for what a computer is. in the 1930s. He also, as sort of the key application of his new theory, he proved that certain problems are not solvable by any Turing machine, right, in any amount of time. Okay, this was the famous unsolvability of the halting problem. Okay, and it built on Gödel's incompleteness theorem, which had been proved just 5 years prior. But it's now a statement that for certain problems, and the famous example is the halting problem. Right, I give you a program, and you have to determine whether it ever stops running. Say when run on a blank input. And and Turing showed that there is no program to solve this problem in any amount of time. And the argument is basically self-referential. Okay, you say, well, suppose that there were such an algorithm, then we could contrive things in such a way that that algorithm would be fed its own code as input, and then it would have to do the opposite of whatever it does. So like if it halts, then it would have to, when run on itself as input, then it would have to run forever. And if it runs forever when run on itself as input, then it would have to halt. And since, that's a contradiction, the only conclusion is that the program can't have existed. Okay. And so, we've known since the beginning of computer science that you can use these sort of self-referential methods to understand something about the limitations, of any algorithm. Right, in a kind of magical way, without having to roll up your sleeves and delve into the details of what the Turing machine is doing. Right, and then in the 1960s, some of the first complexity theorists, like Joris Hartmanis, who passed away recently, and Richard Stearns, managed to go further, and they used similar self-referential arguments to show, for example, that there are problems involving n-bit inputs that are solvable in n-cubed steps, but are not solvable in n-squared steps. Okay, there are other problems that are solvable in n to the fourth steps, but not in n cubed steps, and so on.
Can you give an example?
Yeah, the simplest example would just be, I give you a program, and now you have to decide whether it halts in n to the fourth steps or not.
Okay.
That is solvable in slightly more than n to the fourth steps. But, a sort of scaled down version of Turing's argument shows that it is not solvable in n cubed steps. And basically because if it were, then the program could predict what it itself is going to do faster than it can do it. Okay, and it's kind of like this is like a paradox that a 5-year-old could understand. It's like if I knew for certain whether I'm going to raise one finger or two fingers 10 seconds from now, then I could just resolve to do the opposite of whatever I predicted I would do.
Yes.
Right? And so, so that's not possible.
To you, does this touch on free will?
Some people think it does. I mean, I tend to think that, if there were a computer in another room, and it ran faster than my brain does, and it perfectly predicted what I was going to do before I do it. And, maybe it leaves its prediction in a sealed envelope, but then after I take the action, then we can open the envelope and we can see that it perfectly predicted what I would do. I would say, that would really profoundly shake my sense of free will. Just speaking personally, right? And I would say that based on the known laws of physics, we don't actually know whether that prediction machine can exist or not. Right? It comes down to, questions about how accurately would you have to scan someone's brain? Would you have to go all the way down to the quantum mechanical level? Would that not be necessary? Right? And I would say that the thing that most people don't realize is that this is an empirical question. Whose answer we'll someday know, but we don't know it yet. And that's sort of, what I would advocate as the best sort of empirical replacement for the free will question, right? And if you accepted that, then it's the fact that I myself can't predict my future actions is not really the core of the matter. The question is just whether any machine could do it.
Yeah, why is the sealed envelope important?
Well, just because if I saw the prediction, then I could resolve to do the opposite.
Yeah, so if this machine existed, does it still say something about your free will if you were able to look at it and you could go against the wishes of the machine or the predictions of it?
Well, yeah. You could say if that machine cannot be reliably built, if any attempt to build it consistent with the laws of physics, fails, then that seems to me like about as far as science, could possibly go in saying that, well, there seems to be something that that corresponds to part of what we mean by free will, right? There is this inherent unpredictability to our actions. And conversely, if the machine did exist, then that seems to be, to me, like about as far as science could possibly go towards saying, actually, free will is an illusion, right? Not just in some abstract metaphysical way, but because, here is the machine that predicts what you will do. Look at it, try it out.
Yeah, you had a blog post on Newcomb's paradox.
Yes.
Can you please outline it and then what your proposed resolution is, if it exists?
Sure. A Newcomb's paradox is the thing where, we imagine this super intelligent predictor, just like I was talking about before, that this sort of machine or being that knows what you're going to do before you do it. And it puts two boxes on a table. Okay. And inside of the first box, there might be nothing and there might be $1 million. Okay. And inside of the second box, there is definitely $1,000. And now you have a choice. You can either take the first box only, or you can take both of the boxes. Okay. But now the predictor, the catch is that the predictor, has told you in advance that if it predicts that you're going to take both boxes, then it leaves then it will leave the first box empty.
So it punishes greed.
Yes. Right. If it predicts that you're going to take only the first box, then it puts $1 million in it. Okay, so and let's say that the predictor has played this game with 1,000 people before you, and it's never been wrong, right? So then what do? Do you as the people have actually made it into verbs? Do you one box or do you two box? In the Newcomb paradox, and and there seem to be like basic principles of rationality that that you could use to prove either answer is correct, right? On the one hand, everyone who takes only the first box ends up about $1 million richer than the people who try to take both, right? And by the whole setup of the problem is that that's because the predictor knew, and it's over. But on the other hand, the by the time you're contemplating your decision, the $1 million is either in the box or not, right? And so how could your decision possibly affect what is in the box? It would seem like it would have to be a backwards in time causation, right? And therefore, whatever is in the first box, you're going to have $1,000 more than that if you take both boxes, and therefore you should take both, right? Mm-hmm. So we can prove two contradictory answers. That is the basic setup of a paradox, and and people have argued about this for half a century. There is an enormous literature on this problem, and many different points of view. I had a blog post back in 2006 where I suggested what seemed to me like the natural resolution of this, and since then I've learned that other people have had broadly similar ideas. So some of them do cite that blog post of mine, but my resolution of the paradox was, okay, I think that in this scenario you should take one box, right? You should one box, okay, but the question is why, right? The question is how can we possibly explain how your decision to one box could affect the predictor, could affect whether the predictor puts the money in the box, okay? And now the key is, well, we have to think harder about what the world would be like with this predictor in it, right? The predictor, contains within it a perfect simulation of you, right? I mean, whatever you're going to base your decision on, whatever childhood memory, whatever detail of your brain function, the predictor knows all of it, right? By hypothesis, right? But the way that I would describe that is that the predictor has effectively brought into being a second copy of you, a second instantiation of you, right? And now, the key is that as you're contemplating your decision, whether to one box or two box, you have to think of yourself as somehow, being both versions of you at once, right? Or, perhaps, you don't know which one you are. Right. If you are the simulation being run by the predictor, well, then of course your decision can affect what the predictor does. So you don't even in the scenario that was hypothesized, like, you have to be radically uncertain about where you physically are, about what time it is, right? Like, these are the kinds of things that you have to worry about in a world where there really could be perfect predictors of yourself. Right. A different, a much a more boring resolution would be to say, well, I'm not going to worry about Newcomb's paradox because I believe that this predictor cannot exist at all. Right. It's as I said, I regard that as an empirical question to which we don't yet know the answer.
Two concepts that I see as related are the no cloning theorem,
yes,
and computational irreducibility. So this is something popularized by Wolfram, which I know you know, so I'll get you to explain it to the audience. But the no cloning may have implications that such a machine can't exist because it can't be a perfect copy of you.
Yeah. Okay. So by the way, no cloning and computational irreducibility are two totally different things. We can talk about both of them. Okay. But the no cloning theorem is just a very, very basic fact about quantum mechanics. Okay. And it says that there is no physical operation that you can do that takes as input an arbitrary quantum state, an unknown quantum state, like, let's say a qubit, a quantum bit, a superposition of a 0 and a 1, okay, and that produces as output two identical copies of that state. Okay, so there is no quantum Xerox machine that is possible. Right, the ability to make perfect copies of things. This is fundamentally, a classical phenomenon. Right, it is not true quantumly.
I'm sorry to interrupt. I'm sure you've heard of Leibniz's law of indiscernibles.
Yeah.
Okay. So this isn't that.
No.
This isn't saying like, look.
This is a fact about physics, that could have been false, right? But it is true because for a century, every experiment has told us that quantum mechanics is true, and as long as quantum mechanics remains the basis of physics, then this is true. But it's not something that is a priori knowable. Okay, and so the sense of copying that I mean is copying the information. Okay, so think about classical bits, right? We all know that classical bits can be copied, right? If you have, this has been the bane of the music industry and the software industry.
Right.
If you have a file, right, you can make a copy of that file, right? It won't be, it'll have a different physical representation, somewhere else in your computer's memory or in a different computer's memory, but it will encode the same bits of information.
Okay. So Napster exists because the no cloning theorem is purely quantum?
Precisely. Yeah. So classical information can be copied. Okay, but what we're saying is that in quantum mechanics, even the information cannot be copied. Okay, so quantum, we have to take a step back and say, what is quantum information? Right? It's the basic building block in quantum information is what's called this quantum bit or qubit. Okay, and this is a bit that it doesn't have to be definitely 0 or definitely 1. Once people hear that, then they say, oh, well, then, that just sounds like a fancy way of saying, well, it's either 0 or it's 1, and you don't know which it is. Right. But, we know how to deal with that classically. Right. We could have a random bit, a bit that has like a 40% chance of being 1 and a 60% chance of being 0. And until you look, you don't know which it is. So you kind of have to think about both possibilities. But then once you look, right? Okay, now that is not a qubit, right? Qubit is more interesting than that. Okay, because what the key thing that quantum mechanics says is that to every possible configuration that a system could be in, like, 0 or 1 in the case of a bit, you have to assign not just a probability, you have to assign a complex number. Okay. These complex numbers are called amplitudes. Okay. They're the basic quantities of quantum mechanics. Right. And so for example, a qubit, a quantum bit, might have a square root of a half amplitude to be 0, and it might have a minus square root of a half amplitude to be 1. Okay. Or they could actually be complex numbers, a real plus an imaginary number. Okay. And now when I make a measurement, then these amplitudes convert into probabilities. Okay? And the way they do that is one of the most famous rules in all of physics. It's called the Born rule. Okay. It says that the probability that I see a particular outcome is equal to the square of the absolute value of the amplitude for that outcome. Right. So if I had like an equal superposition, 0 plus 1 divided by the square root of two, the qubit 0, plus the qubit 1 divided by the square root of 2. Okay. And then I measure it, then I'm going to see 0 or 1 equally likely. Okay. But there are other things that I can do besides just measuring the qubit to ask it whether it is 0 or 1. Okay, I can, when the qubit is isolated, then these amplitudes can change in time by rules that are not familiar to our experience. In particular, I can take the list of all the amplitudes of all the possible states, and I can do something to my system, my particles or whatever, that has the effect of doing a linear transformation on that list of amplitudes. Right. So this you could say in some sense what quantum mechanics tells us is that the operating system of the universe is linear algebra. It's matrices and vectors, right? My states are these vectors of amplitudes, these lists of complex numbers. My time evolution, the way the state changes over time while it's isolated, is that I apply what's called a norm-preserving linear transformation, or also called a unitary transformation. Okay, these are like linear transformations, matrices that always map unit vectors to other unit vectors. Right, so they always preserve the length of the vector. Okay, but an example would be a rotation. Right, like I could take a qubit, that is some intermediate state between 0 and 1. Right, somewhere on like the unit circle where here's 0, here's 1, here's minus 0, here's minus 1, and I could rotate by a certain fixed angle. Right, or I could reflect about an axis. Hey, these are unitary transformations that I can do, and then I measure, and then I measurement is a destructive operation. It sort of collapses me to a single outcome. But now, the key phenomenon that told physicists that, that the world works this way in the first place a century ago. Okay. And that, and it is sort of the signature that something quantum is going on, is called interference. Okay, so now if I want to know, let's say, how likely is a particle to hit a certain spot on a screen, right? Then, I have to calculate the amplitude for that thing to happen, right? And then take the squared absolute value, and that gives me the probability. Okay, but the amplitude is a sum of a whole bunch of contributions. Okay, one from every possible path that the photon could have taken, or the particle could have taken, in order to reach, this endpoint, right? And now, if some of those paths that it could have taken make a positive contribution, and others make a negative contribution, then they can interfere destructively and cancel each other out. Meaning, like, the total amplitude will be 0, and then the particle will never be found there at all. Right. Whereas, and here's the even crazier part. If I close off one of the paths, like the famous 2-slit experiment, where there are 2 slits that this particle could go through, if I block one of the 2 slits, well, now I only have a positive contribution or only a negative contribution, depending on which slit I blocked. So now the particle can appear at that endpoint. Okay, so to say it again, by decreasing the number of paths that a particle can take to get somewhere, I can increase the chance that it gets there. Okay. That is something that, just, forget about all the low level details of physics, right? That could never happen if the world were described by conventional probability theory, right? That is sort of the sign that we have, to actually describe what physics is doing, we need different rules of probability. Okay, which is a much more fundamental thing than you might have imagined the laws of physics even talking about at all.
Yeah.
Okay, but they do. And so now, okay, so now we can come back to the no cloning theorem since you asked about it. Now, a qubit is going to have some state like a times, the qubit 0 plus b times the qubit 1, right? Where a and b are amplitudes. Okay, so the state of one qubit is described by a two-dimensional vector, a list of two complex numbers, a and b. Okay, now what would it mean to make a copy of the qubit, right? It would mean that, well, now, what at the other end, I should have two qubits that are both in the state A0 plus B1, right? Okay, and now, okay, and the way that in quantum mechanics, the way that we describe sort of two systems that are just sitting there next to each other and that are, separate from each other, that haven't interacted, right? It's a mathematical operation called the tensor product. Okay, but it basically just means, we take like component-wise multiplication. So if I have A0 plus B1, for my first qubit, times A0 plus B1 for my second qubit, okay, then I can, just like in middle school algebra, I can expand it out and I can say that's an amplitude of A squared for the qubits to both be 0. That's an amplitude of AB for the qubits to be 0 and then 1. It's an amplitude of AB for the qubits to be 1 and then 0. And it's an amplitude of B squared for the qubits to both be 1, right? So now I have a new vector. I want, A squared, AB, and B squared. Okay. But now that we know that, now we've proved the no cloning theorem. Okay. Why have we proved it? Well, because that transformation that we just asked for is a nonlinear transformation. Okay. The amplitudes, A and B, were not replaced by linear functions of A and B. They were replaced by nonlinear functions such as A squared or, B squared. And that is a thing that unitary evolution in quantum mechanics just cannot do. Okay. And so, the way to, there are other ways to prove the no cloning theorem. Okay. But, one way to prove it is really as simple as that.
I see. Now, computational irreducibility. And then also what all of this has to do with Newcomb's paradox.
All right. So, I mean, computational irreducibility is just, a term that Stephen Wolfram uses for, I would say, a basic phenomenon that was, known to many people before Wolfram. He likes to, treat everything as his invention. But, it is, the fact that for many systems that are computationally universal, like we cannot figure out how to predict their behavior faster than just by simulating the whole thing, right? Mm-hmm. So there are in some sense science has gotten all as much leverage as it has over the past 400 years because often we can model a system, by something that is simpler than the system itself, right? So the orbits of the planets around the sun, the orbit of the moon around the Earth, right? Kepler said, these look to me like ellipses, right? And then Newton explained, from a single simple law of gravitation and from laws of motion, right? He explained why they should look like ellipses. Right. And then, you can predict, in some cases what the planets are going to be doing millions of years from now. Right. Because, the system is simple enough. Okay. But, there are many other systems, we could take a lava lamp, for example, or the weather. right? Where there is just so much dependence on the fine details of the system state at any one time that if you try to run a prediction to a future time, then your prediction will before long diverge from reality. Okay, this is the famous butterfly effect, right? That unless the exact state of every particle and can then feed that into your computer, right? Then like a small error, whatever small error you make in knowing the current state is going to blow up exponentially over time. Okay, that's the basic phenomenon of chaos. And computational irreducibility, I think it's just the term that Wolfram uses for like the analog of chaos in discrete systems like cellular automata.
Great. And so what does that have to do with free will and Newcomb's
Well,
chaos?
okay. I mean, what I would say is that if there is some deep reason why the prediction machine cannot be built, why the Newcomb predictor cannot exist, then the only candidate that I can put forward, based on the physics and neuroscience and so forth that I know about, is to say, well, maybe in order to make a well calibrated prediction of what a person is going to do, you would really have to know not just like a crude approximation of the state of their brain, which could mean like knowing the connectivity pattern of the neurons, knowing the strength of each synaptic link, and so forth, right? Maybe that's not good enough. Okay. Maybe you need to know is this individual neuron going to fire or not? Right. At this time. Right. Because, a single neuron firing or not firing could certainly trigger a cascade, of chaotic effects, right? Maybe if this neuron fires, it causes 10 neurons to fire, which in turn cause 100 neurons to fire, and so forth. And before long, you're going, going into industry rather than becoming a professor, or
Right. Okay.
you've made a different choice for your or you're marrying a different person.
Yeah. So a cosmic ray is responsible for Scott not being a quant.
This is the question, right? Like what is the smallest change that you could have made? And this is a standard trope of like time travel stories in science fiction, right? Like when you go back in time, if you change even the tiniest thing, like usually they're like, oh, we have to walk very carefully and not kick any of the rocks. It's like, okay, that's kind of silly. If you believe this at all, then the very fact that you're there, disturbing the air molecules, it's like, forget it. You've already completely changed the future, right? But okay, now if we really need to know whether a single neuron, fires or not, well, we know that the sodium ion channels, that control that, right, are modeled, in neuroscience by something called the Hodgkin-Huxley equation, okay, which is a stochastic differential equation. Okay, so it has a noise component, right? And the neuroscientists would probably say, well, we just treat it as thermal noise, right? We just treat it as a bunch of molecules are bumping around randomly, and that somehow sometimes it makes the sodium ion channel open, and other times it makes it close, right? But if you really needed to make an exact prediction, well, then maybe you need to know the states of all these particles so precisely that you would have to violate the no cloning theorem, right? So let's be clear. I don't know if that is true. I regard this as at least partly an empirical question, right? Someone could address it by trying to build a brain duplication device, trying to build a prediction machine, right? And if they succeed, then we'll know that the answer was one thing. Okay, but there is also a philosophical question here. I should admit, of like how good or how accurate does the copy have to be before you will accept that copy as sort of being a new version of you.
Right.
So this is the famous thought experiment here is like imagine that someone has built a teleportation machine, right? And that can teleport you to Mars. Okay, you can visit Mars in only 10 minutes transit time, right? But the way that it works is that you will get Your brain will get scanned in as pure information. That information will get sent to Mars. On Mars, a machine will reconstitute you from that information. And then the original version of you on Earth, well, that'll just be painlessly euthanized or something, right? And so now, the question is, do you agree to go in that machine, right? Is that a means of travel that you are comfortable with, right? And I think, well, it might, depend on the details of, just how accurate, is this copy, right? Is it, is it really perfect? Is it just good enough? And these are, there have been philosophical thought experiments about this kind of thing for generations. Okay. But, we can already see with, GPT, for example, with the AIs that have come online within the last few years, that, these questions are going to come up, like, take a person who has some giant corpus of work, tens of thousands of postings on the internet, right? And then, you can train a model, you could train a language model to emulate that person, as well as it can. As, character.ai and companies like that are already doing in a kind of crude way. They let you, talk to Einstein, talk to Taylor Swift, talk to Socrates or whatever, right? But I didn't find it that engrossing. They all kind of sounded the same to me. They all kind
Right.
of sounded just like different language models. Okay, but imagine that gets better, right? Imagine that like you make this doppelganger of yourself, and then you lay in bed all day and you get up and you see what it's done, and you say, yeah, those are totally the things that I would have done. Right? How good does it have to be before you accept it as a replacement for yourself?
Do we need to go as far as a teleportation thought experiment to Mars? Because even when you move a sub-millimeter amount, it could technically be that you just got destroyed in an instant and then was just reconstituted a sub-millimeter further.
Well, yeah, so there is that philosophical question, right? Of are we constantly just being destroyed and recreated, or should we think about it that way? Now, we certainly in ordinary life, we don't think about, I get on a bus, I get on a plane, I move around as something that is destroying and reconstituting me, right? But now, if you really want to get confused about this, you can think about a quantum teleportation, right? So there is a protocol by which you can transfer, a quantum state from one place to a different place. Okay. If you have two resources, number one is just classical communication, the ability to send conventional bits, like let's say over the internet, for example, right? That's pretty. And the second resource is you need pre-shared quantum entanglement. Okay, so you need like the sender and the receiver location to have pre-shared entangled quantum states. That were sort of correlated with each other beforehand. But if you have both of those things, there is this amazing protocol that was discovered 30 years ago. Okay, that where you measure you measure your quantum state. Let's say Alice, over on the left side, measures her state, as together with her entangled particle, and then she gets 2 bits of information that she sends over the internet to Bob. And then Bob, using those bits, applies some correction operations to his entangled particle. And now, voila, he now has exactly the same quantum state that Alice had before. Okay. Now, you might say like, how is this possible? Was information sent faster than light? Well, no, it wasn't, because, we had to send these classical bits, right? And those only moved at the speed of light. So, this is consistent with relativity. And then the next thing you could ask was, well, did this violate the no cloning theorem? Right? Because I had my quantum state, and now somehow a new copy of the quantum state has popped up over at Bob's end. Okay. But the key is, in order for this to work, Alice had to make a measurement that destroyed her copy of the state.
And does Alice know her copy of the state before?
No, she does.
She doesn't even know what she's sending?
Right, exactly. She doesn't have to know.
She doesn't have to know, or she can't know?
She can know, but she doesn't have to.
Oh, I see.
Okay. And then Bob just ends up with a new copy of of the same state, whatever it was. Okay, and so you could say, would you agree to be quantumly teleported to Mars? Right. Well, in that case, that sounds potentially better or safer than just being sent as classical information, because in that case it really is the same quantum state that would be reconstituted on Mars, right? Just like it would have been if you had just gotten into a spaceship and traveled to Mars in the conventional way.
Yeah. All right, great. Do you have a preferred interpretation of quantum mechanics?
Well, there is
Actually, if your views on this have changed, then it would be great to outline what they were prior and what changed them.
Okay. I mean, usually, when I teach this, teach quantum mechanics to undergrads in my, quantum computing and information class, I try to teach it like comparative religion. I try to not tip my hand about, which interpretation I'm leaning toward, but I've discovered something interesting over, in recent years, which is that, it's really hard to not, make the majority of the students into many worlders. Once they see the pros and cons laid out, then kind of the and then we ask, as an ungraded question on the final, we ask, what's your favorite interpretation, and then consistently a majority say that there are many worlders. Okay, so just to back up, many worlds interpretation is just the one that says, that the wave function, which is this list of amplitudes, for all the possibilities, that you could get, that is the fundamental reality, right? That is, what the universe is. It is this list of amplitudes, right? And, it evolves in time just by this unitary evolution. And, the many worlders would say, that measurement, is not real. Right. Measurement is sort of our local perception, from our local point of view. Right. But it's not really a fundamental law of physics. Okay, so if there's a sense in which that is the mathematically simplest or nicest picture that you could have, right? Where it's just all unitary evolution, which is continuous, it's reversible, it's it's deterministic, right? You don't have these weird probabilistic, irreversible jumps. You don't have any of that. Okay, but the cost for saying that is that now if, let's say, there's some qubit that's in a superposition of 0 and 1, and then we make a measurement of it. Okay, then the way you have to describe that, by unitary evolution, is that the whole system, consisting of the qubit and the measuring device and me, are now going to evolve to a new quantum state. Okay, and that state will have two components, and in one of the components, the qubit is 0, and the measuring device registered it as 0, and my brain, I looked at it and I saw the 0, right? And in the other branch, the qubit was in the state 1, and the measuring device registered it as 1, and my brain, saw that. Okay, so you're led to this prediction, that the universe is sort of constantly splitting into branches, as it were, or at least what we would regard as sort of different, approximately classical universes. Okay, and where our lives could turn out differently, right? And so in some sense, like if you just treat, if you were to treat like the qubit plus, all of the atoms in the measuring device and all of the atoms in your body as just all quantum mechanical systems, right? All just obeying the same Schrodinger equation, the same laws of unitary physics, and nothing ever gets singled out as being an observer or having this sort of special role, then like that is the prediction that that you would get, and so now, like, in some sense, the whole interpretation problem of quantum mechanics is, what do you do with that fact? Okay. And so now, that there are, a few different approaches. The original approach of, Niels Bohr and Werner Heisenberg and most of the other founders of quantum mechanics was to say, then, this wave function, this list of amplitudes is not real, right? It's just a mental device in our heads that we are using in order to calculate the probability that we will see this outcome or that one, right? What is real is what we see when we make a measurement. Right.
Yeah.
And so then, they would tend to say, there is the classical world that we live in. And then there is the quantum world, which is the subatomic world. And measurement is somehow an interface between the two worlds. Right. But then the problem that's called the Copenhagen interpretation. Right. But the problem that Copenhagen has always had is, where do you actually draw the boundary between the quantum world and the classical world? Right. And like nowadays we can take much bigger systems and we can put them in superposition states, like even molecules with, thousands of atoms in them. We can put in a superposition of going one way and going another way. Nothing as big as a Schrodinger cat, yet, but like after a century, no one has discovered any fundamental obstruction to, scaling up superpositions arbitrarily. Right. And quantum computing, feeds into this discussion as well, because if you can build a scalable, error corrected quantum computer, then you could have like millions or billions of qubits that are all, in a superposition of two different states. Like, if you even loaded an AI program onto that quantum computer, and if, the AI were conscious, then it could even be in a superposition of thinking one thought and thinking a different thought. Right. So, which was the original thought experiment that sort of led David Deutsch to, propose the ideas of quantum computing in the first place in the late 1970s. Right. So the question is, like, where does the buck stop? Right. And the Copenhagen approach has basically been to say, well, there are certain questions that you're not allowed to ask. Right. You just, to say that, we know a priori what it means to measure something and get a classical outcome. This is just a precondition of doing science. And so we have to just assume this. Right. And, you can say like that was an answer that was bound to not satisfy everyone forever. Right. But you can say that's sort of option one. I view it as kind of the giving up option, right? You just say, the theory, it works for experiments, and we're not going to treat the whole universe, including ourselves, quantum mechanically. We're not even going to try to understand that. And then a second approach would be to say, yes, there is this whole wave function, right? There is this whole list of amplitudes for every possible outcome. But also, there is one particular branch that is the real one, that is the one of actual experience. Right. And so like you have this giant ocean of amplitudes, but then there's also a cork in the ocean that just gets pushed around by the waves, right, in a way that matches the predictions of quantum mechanics, the Born rule. Right. That is what David Bohm tried to do, and Louis de Broglie. Right. This is called the pilot wave, or the de Broglie-Bohm interpretation of quantum mechanics. Okay. And and there were many different versions of it, because you can write down like thousands of different such rules for how the cork is going to go that will all end up with the same predictions for any experiment that we can do. Okay. And then, a third point of view, would be, many worlds, where you just bite the bullet. Okay. And you say the wave function is real, and I refuse to introduce any additional ingredient, like any cork in this ocean. Right. Which means I'm not going to regard the other branches as any less real than my branch. Right. I regard all of them as existent. Right. I can't talk to the other branches. The fact that quantum mechanics is linear is the thing that prevents me from communicating with the other branches. right? But if they're there in the equations, if they're there in the theory, then I'm going to say that they're just as real as whichever branch you and I happen to experience. And then, the fourth outcome, or sorry, the fourth option would be to say, well, none of these ideas are any good. Right? None of these interpretations, is acceptable, and therefore, there must be something wrong with quantum mechanics itself, right? And hopefully, in the future, we'll discover a better theory of physics that says, okay, here is when the quantum state collapses. It happens when it gets this big or this massive, and there will just be some objective, testable law of physics that describes the collapse process. Okay, now that would be something new, right? That's not an interpretation. That would be a new and different physical theory that would overturn quantum mechanics as we know it today, right? But you can say, well, then that has to be the truth. Quantum mechanics has to just be an approximation to some better theory that hasn't been discovered yet. So, you ask, what I'm partial to. I'm kind of partial to an idea by the physicists Lenny Susskind and Raphael Bousso from a decade ago, which is that cosmology might be an important part of the story, right? Mm-hmm. So, like you could say the big, one of the main problems, for anyone who is trying to interpret quantum mechanics is to specify, when does a measurement happen, right? When does the buck stop, and when should I regard, this superposition of outcomes as having resolved into one or the other definite outcome, right? Like the the many worlders, might say, well, there's no one right answer to that question, right? It's kind of like asking, like, how many grains of sand do I have to put together until it's a heap of sand?
Exactly.
Right. But even they might want a rough and ready rule for when we can treat an outcome as definite. Okay, and now here is one possibility for such a rule. Okay, so when you make a measurement, right, it's not just your brain that becomes entangled with the qubits or the particles that you measure, right? It's the air in the room that you're in, right, and the radiation in the room, right? There's a butterfly effect that happens, right? Like each thing, each particle starts knocking around the nearby particles, and so there's a whole bubble of effects of whatever the outcome of that measurement was that spreads outward, from you, no faster than the speed of light. But as soon as the information gets encoded into photons, then possibly this sphere of effects is expanding around you at the speed of light, right? And once the information about which measurement outcome you saw is encoded into photons that are leaving the Earth, right, and that are flying away from the Earth at the speed of light, right, which eventually they will be, then you could say, well, even in principle, we could never catch those again, as we would need if we wanted to recohere the superposition. If we wanted to show that see any effect of the other outcome of the one that we didn't measure. Right. So, in order to get interference, you have to collect all of the qubits that were affected. Right. And, if many of those qubits are flying away from us at the speed of light, well, then you can say, how could we ever catch them again? Well, if there were some extraterrestrials who had thought to enclose the solar system in perfectly reflecting mirrors, right? Well, then, okay, then the photons are going to bounce back, and then maybe we could recohere. And we could see that this is still a quantum superposition, but I will assume that aliens have not done that, right? That does not seem to be the case in our universe. Okay, and then you get into questions about cosmology. So, there's this cosmological constant that was discovered in 1998. Right, which is also known as the dark energy, right? It's the thing that is pushing the galaxies away from each other at an exponential rate, right? And this has been, one of the, the most important discoveries in all of physics for decades, right? And certainly in cosmology, right? The fact that this dark energy exists, what Einstein a century ago called the cosmological constant. Okay, it's actually not zero. We now know that, right? But now, if that constant had been negative, right, which it could have been, okay, a universe with a negative cosmological constant is one that in some sense does have a reflecting boundary, right? It's called an anti-de Sitter universe. Okay, and in that kind of universe, like, we would be like sort of trapped in a bubble where everything would be unitary, right? And where, like, any photons that are flying away from the Earth, eventually they can come back, right? And so no loss of quantum coherence would truly be permanent in that kind of universe. Okay, but since 1998, we know that we don't live in that kind of universe, right? We live in a universe with a positive cosmological constant, a de Sitter universe. Okay, and in that universe, things really, at least as far as anyone knows, no one knows for sure, but it's, it seems possible that things can fly off to infinity, and we could just take that as our criterion for when a measurement has happened. So in some sense, we could say, like, it doesn't, we could sort of harmonize the many worlds and the Copenhagen points of view by saying, like, yeah, at some formal level, yes, we there is this whole wave function of the universe, or, we're willing to talk about it. That does include all of these branches where all these other things happen, right? But there's also a criterion, for loss of quantum coherence, right? The photons flying away from me at the speed of light, where after that happens, then I might as well say that the other branches are gone, right? They are now not empirically accessible to me, even in principle.
So, in other words, when you're teaching this in the comparative religion sense, you're the Baha'i faith. Each of them has some semblance of the truth. Now, what was the name of the Susskind interpretation, or the Susskind theory?
I think they called it the multiverse interpretation or something. And by the way, I just saw Lenny Susskind a couple weeks ago, and he doesn't seem to believe his own interpretation anymore. But I still like it, though. Yeah.
Great. So the multiverse interpretation is separate from the many worlds, because those sound similar.
That's right. Yes.
And the many worlds, when you said that you measured, forgive the pun, your students at the end, and then they said that they like the many worlds, 80% or so, say.
I think it was probably more like 55% with the rest.
Okay, so a majority still.
With the rest split among Copenhagen, Bohm. I allowed, like, agnosticism, or what does it even matter, or shut up and calculate, or or that there has to be new physics. I allowed all those things.
Yeah, it's surprising to me that number 4, the provisional one, that hey, we don't have the current fundamental law, and so who cares about it, isn't more popular, given that gravity isn't integrated into quantum mechanics.
I mean, it does have adherents, right? Roger Penrose is one very famous adherent, right? But I think he sort of hurts his case by tacking onto it like a whole enormous chain of speculations, right? That he thinks that quantum gravity causes an objective collapse of the wave function, and this collapse is uncomputable. It cannot be simulated by a Turing machine, and the microtubules in our brains are somehow sensitive to this quantum gravitational collapse, and this is implicated in consciousness. Right, so that's the Penrose view, and you can say, like, even if you might go with him, like, to the first stop of that train, most of us are going to get off by the before the later stops, right?
Yeah. Okay, we're going to explore uncomputability shortly.
Okay.
So, what I was getting at was, did you measure the students initially and say, hey, what is your preferred interpretation, in order for you to establish a difference?
Yeah, that's a good question. Like to do a controlled experiment, you ought to do that. The trouble is that until I expose the students to all these interpretations, they don't even know what they are. Right.
Yeah.
Most of them have not even heard of them, or if they have heard of them, then I'm not sure if they could define them.
The reason is because in the popular press, many worlds is prominent. And so it may just be an effect of, hey, I like Sean Carroll. I listen to his podcast.
Yeah. Well, Sean makes very, I've, he's been a good friend of mine since, 2006 or so. And I think he does make very strong arguments for many worlds. And I say that even though, I am not nearly as hardcore of a many worlder as Sean is.
Isn't there still the issue of having a globally well-defined measure in order to even state what the probability distribution is of different branches of the wave function? But can you explain what that is?
Yeah. So, you could say that the basic problem for, if you want to be a many worlder is you have to explain, well, why do we only perceive one world? Right. And not only that, but why do we perceive, each world with these particular probabilities, these Born rule probabilities. Right. But now, I have to say, like, I don't regard that as like a problem for only the many worlds interpretation. All right. I think that it is, you could ask the same question with any interpretation. Like, where did these probabilities come from?
Yeah.
Right. It's just that question takes on a different character depending on which interpretation you like. Right. Because, if you believe in new physics, then you have to postulate some new law of physics that will then give rise to these probabilities. Right. And, you can check, whether it does or it doesn't. And, ideally you wouldn't just, stick them in, but, in physics, it's always better if you can derive something, right. Rather than, rather than just assuming it from the outset. If you are a Bohmian, right? Well, then, you've just, you postulate a rule for your hidden variable, for your quark in the ocean that happens to always give you agreement with this Born rule, right? But then you could say, why should it have been a rule of that kind? Right. And then, will we, if we started out in some other distribution, would we reach that Born distribution as an equilibrium? Right. So that's what the question looks like to a Bohmian. To a many worlder, the issue is that a many worlder is committed to the view that all of the outcomes are real. Right. All of the outcomes are experienced by someone. Right. And so then they have to say, then what does it even mean to say that this outcome has this probability and that one has that probability? Right. Like, how do you even make sense of that statement? It's like, you have to imagine that there's like all of these beings are real, but somehow, one of them is going to be picked to be, your experience. Right. And so somehow there is some, meta law that governs that. Right. And so there is a long history, since Everett himself in the 1950s of many worlders, trying to or claiming to derive the Born rule, right? Derive the probabilities. Okay, they always have to make some auxiliary assumption, in these derivations, right? Because it's like you're starting with a picture that has just the wave function, that has no probabilities in it, and then in the end, you get a statement about probability. Right. And so, there has to be some step where you're just postulating that, yes, something is random. Right. And for a many worlder, what that kind of looks like is, it's this thing called indexical uncertainty or self-locating belief. So like basically, imagine that, you didn't know your own blood type. Right. Like, you just hadn't gotten tested yet. Right. But then you say, well, look, there's this many people in the world who are type O. There's this many people who are type A. Right. So I'm going to just assume that I was, a randomly chosen person. Right. And there's something fundamentally weird about that. Right. As soon as you start thinking about yourself as chosen randomly from the set of all people.
Yeah. There's also a reference class issue.
Yeah, exactly. Then you can start wondering about things like, why was I born in the, late 20th century as opposed to, in medieval Spain or at some other time, right? Why am I on Earth? Why am I not an alien on a different planet? Right. And, it's not obvious if these questions have well-defined answers at all. Right. But what the many worlders need to do is to say, there are all of these branches of the wave function that are all real. They all have real copies of you, but now you have to think of yourself as as a randomly selected member of that ensemble, right? And then once you decide to do that, then you actually can give many mathematical arguments that like the Born probabilities are pretty much the only probabilities that would make sense, right? Like you can show that like any other choice for what the probabilities would be, like if instead of the absolute square of the amplitude, suppose it were the absolute cube of the amplitude, right? Or the absolute value to the 2.8 power, or something like that, right? You can show that would give you like nonsensical things. It would lead to faster than light communication. It would lead to sort of massive violations of the laws of physics that we understand. So you can kind of give arguments for once you've decided to put a probability distribution over all these branches, why it should be this particular one, right? The harder part is to say, why should there have been a probability distribution at all?
Now, it's been a while since I've studied this, but it's my understanding that the space of pure quantum states is a projective Hilbert space, which is a Kähler manifold. The symplectic structure gives rise to the dynamics, and the complex structure gives rise to the superpositions, and the Riemannian metric gives rise to the probabilities.
That's probably all true. Those are already much fancier words than the ones that I ever use to talk about these things.
Right. Well, fancy words with a specific mathematical meaning. Some say that computability or quaternions are fancy words.
Right. Exactly.
Yeah. What I mean is that when one says, well, where does the Born rule come from? In a Kähler manifold, if you have two of those structures, you get the third. So why isn't the question then, well, why do we have a complex structure? Or why do we have symplectic?
That is a different superb question. You could say, like, why should quantum mechanics have been based on complex numbers? And you actually can define a variant of quantum mechanics that would only use real amplitudes, right? And that version turns out to be pretty good for many purposes. Like it would lead to exactly the same power of quantum computers, as our ordinary, complex quantum mechanics. Right. It would lead to, basically all of the same, information and communication protocols, such as quantum teleportation. You'd have the same no cloning theorem, the same, all of that stuff. It's just that there are certain things that would be less elegant in the universe with real quantum mechanics. Okay. And, some of those arise just because the real numbers are not algebraically closed. You can't take square roots of them. Right. And so like if I have a unitary transformation that, operates over, let's say 1 second of time, and now I want to know, okay, but now what was the piece of it that operated only over the first half second? Right. Well, then, as long as I have complex matrices, then I can just take a square root. Right. And, I'll get an answer to that question. Okay. With real matrices, there might not be a square root. In the same number of dimensions. So for example, there's no 2x2 real square root of the matrix 1, 0, 0, -1. Right. That would be an example. Right. And we can see that because it has a -1 determinant. Right. So that breaks, various things about the way that physicists use quantum mechanics. And then, there are other more subtle things that also break, like the number of parameters that you need to describe a composite state. In complex quantum mechanics, it's exactly just the number of parameters that you need to describe the first piece times the number of parameters that you need to describe the second piece. Okay, but in real quantum mechanics, that's no longer true. By the way, it's also not true in quantum mechanics based on quaternions. Right.
Right. Okay. This is interesting.
With real numbers, you get an undercount. With quaternions, you get an overcount, and only with complex numbers does it work out exactly right. Okay. So
I never heard about the overcount.
Yeah. So there are these subtle things that just work out perfectly when quantum mechanics is defined over the complex numbers. But I've asked mathematicians this question, like if you were God, designing the universe on a blackboard, right? Like why would do you know why you would have chosen the complex numbers for this? The in some sense the deepest laws of physics that we know. And the mathematicians were like, well, come on, they're algebraically closed. They're why wouldn't you want them? Right.
Yeah.
So
I think you said this, that we used to think there were two logical operations, and or, but then we found out with quantum mechanics there's complex linear combinations of a third.
Well, yeah, okay. So I was saying like in terms of how you can combine multiple possibilities, right? Like it's when someone says that an electron, for example, well, it's not in its ground state, it's not in its excited state, it's in some kind of superposition of the two, right? Often, the first thing that they think that you mean is, well, then you must be saying that it's in both simultaneously, right? And and the trouble is, if you take that too literally, that it leads to, like, for example, a vision of what a quantum computer is, where it would just try all of the different solutions in parallel, right? And that's wrong, right? That's just like, that leads you to like leads people to importantly wrong expectations of how useful a quantum computer would be if they really think that it could try all the answers in parallel, in the naive way, right? So then you correct that, and then they say, so then what you must be saying instead is that the electron is in one state or the other, and we just don't know which one. Right? It's either in the ground state or these, but no, we're not saying that either. In some sense, like, it's a different ontological category that, there was no, ordinary English word for, because no one needed it before the 1920s, right? And that new ontological category is, you have a complex linear combination of the two things.
Do you believe there to be a fourth ontological category that involves the quaternions?
I mean, you could define quantum mechanics over the quaternions, or over the reals, for that matter, and that would give, a subtly different answer. So, yeah.
But what would that look like?
So quantum mechanics over the quaternions turns out to be sick in various ways. Like, it's sort of
sick
not
as in cool, or sick as in
well, let me tell you what I mean, and then you can decide. Sure. Okay. At least naively, in quaternionic quantum mechanics, you could send information faster than light. Okay. And in fact, like, if Alice and Bob are far away, right, then it could, even if Alice is on Earth and Bob is on Mars, like, it could matter which one of them does an operation first, right? Does Alice act first, or does Bob act first? And this is because the quaternions are non-commutative, right? So, it matters in, even for separated events, it can matter, sort of which operation we put there first. And now this is in flagrant contradiction with special relativity, right? Which says that, when two events are, space-like separated, then it can't matter in which order, they're done, because, to some observers, Alice will be first, and to other observers, Bob will be first. Right. And these two perspectives have to be consistent with each other. Okay. So quaternionic quantum mechanics breaks that, because the quaternions are not commutative. So if you want to believe in it, then you need some way, of making that effect go away at large enough distance scales, or something like that. There's a physicist named Steve Adler who spent decades trying to make that work. But, I talked to him a few years ago, and he said that he doesn't really believe it anymore. So, and then, okay, but now real quantum mechanics, like I said, that one does make a lot more sense. But, a real superposition, philosophically, I would think of as almost the same sort of thing as a complex superposition. They're just kind of different in detail.
No, the octonions have been chopped liver in this conversation.
Yeah, octonions don't even get started, right?
Yeah. Do you mind getting a tiny bit started? Just explain, because that's a popular subject.
Well, okay. The octonions are, so there are these four, what are they? Complete division algebras.
Norm division
algebras. So, excuse me. The reals, the complex numbers, which have two parameters, the quaternions, which have four parameters, and the octonions, which have 8 parameters. And, and like naively, you would expect that it would, it must just keep going after that point. But, it was a very important theorem from the 19th century that says that these are the only 4. Right. Uh-huh. So it's sort of the progression stops after that. So there are these 4 norm division algebras that are kind of special. But, as you go to the larger and larger ones, you lose certain properties. So like, the reals are ordered, right? The complex numbers and beyond are not ordered. Okay, but with the complex numbers, you could say, you lose something, but you gain something, right? You gain that they're algebraically closed, right? But now when you go to and the complex numbers are also, commutative, they're associative, they satisfy pretty much all of the basic properties that you would want in algebra, right? But now, with the quaternions, that already starts falling apart because the quaternions are associative, but they're not commutative. Okay, so A times B can be different from B times A.
Which doesn't sound terrible because non-commutativity is a hallmark of quantum mechanics.
No. I mean, look, and octonions still have, they have applications in, even in computer graphics, in math and physics. They are actually used, right? As I said, if you want to use them as amplitudes in quantum mechanics, then there is stuff that goes wrong. You have to then somehow make that consistent with relativity. Okay, but now the octonions are not commutative and they're not even associative. Right. So, it's funny. It's like, in like fifth or sixth grade, right? Kids learn all these terms, this is the commutative property. This is the associative property, right? But until you've seen any examples of things that are not commutative or not associative, then this is just a bunch of words to memorize.
Mm-hmm,
right.
Mm-hmm.
I think that the time when you want to teach these terms is the time when you want to teach things that don't satisfy them. Right. I mean, for my daughter, my 10-year-old daughter, just the other day, I gave, the example of something non-commutative, getting dressed, right? Putting your
Yes.
putting your pants on and then your underwear is not the same as the reverse. Right. And so there are examples for non-commutativity that even a small child can understand. Non-associativity is a little bit harder.
Well, you're lucky this camera is only here. Otherwise, you'd see that I don't pay much attention to the non-commutativity of the pants and underwear. Before we get on to consciousness, I want to talk about IIT and I want to talk about P versus NP, P equals NP, which, by the way, when I learned it as a teenager, I just learned the equation P equals NP, and I'm like, when N equals 1, it's obvious.
Right. Or P equals 0, right?
Yeah, right. Yeah. Anyhow, I want to get to that. But we mentioned Wolfram before, and Wolfram has a physics project. And so I'm curious if you had a chance to go through it and what your thoughts are.
Yeah, I mean, my basic objection to his project is the same as what it was 21 years ago when, one of the first things I ever wrote as a student was a review of his A New Kind of Science book. And, what I spent half of that review doing is just explaining why, his kind of model cannot account for the known phenomena of quantum mechanics. Right. And this is not a fuzzy statement. Like this is a thing that one can prove. Right. So, he, what he wants basically is to, reduce everything in the universe to cellular automata, right? To some, a bunch of bits, maybe at the Planck scale or something like that are, undergoing some sort of simple computational rules, and that far along, yeah, I think, that's great. That's like, the whole physics community would like that, right? They would like, especially a theory of quantum gravity that would explain why, what's called the Bekenstein-Hawking entropy is finite, right? Why are there only finitely many degrees of freedom in a black hole, right? Or apparently in any physical system, right? Like, what is it, when you get down to the Planck scale of 10 to the minus 33 centimeters or 10 to the minus 43 seconds, right? Something seems to break in our picture of a smooth, continuous spacetime. Okay. And we can see that from thought experiments where, for example, if you tried to, build a clock that was more reliable, that could measure time more finely than 10 to the minus 43 seconds at a time, then your clock would take so much energy that it would just collapse to a black hole instead.
Right.
Right. So, okay. So there are these thought experiments that tell us that sort of something breaks at the Planck scale. But, can you actually explain that by giving a theory where space and time are discrete or sort of discrete at the Planck scale, right? That is I would say, a central part of the problem of quantum gravity. Right. But now Wolfram, wants to do something else. Okay. He wants to say, no, it's not that we have quantum mechanics with a finite dimensional Hilbert space and, with a discrete space and time. He wants to, in some sense, get rid of quantum mechanics, right? And have it be a classical cellular automaton, right? And then the problem is, well, we have, in a mountain of evidence that quantum mechanics is both true and unavoidable, right? And so, what does he do with that evidence, right? And and he kind of hand waves it away, right? This is the key problem, right? He in A New Kind of Science, he said, well, it's true that there are these experiments that you can do on entangled particles, that could be very far away, that lead to these phenomena like the violation of the Bell inequality, right? Which is, famously a thing that sort of you could not explain in a classical universe, right? And that's sort of a very crisp statement, right? Like, it doesn't matter what additional assumptions you make, as long as they're reasonable ones or sort of sane ones. You say, I'm, Alice and Bob, who are far away from each other. They measure their halves of, of this entangled pair, and the statistics of the outcomes could not have been explained by any theory where the particles just secretly agreed in advance on, whether to be spin up or spin down or whatever, right? It can only be explained by saying, well, until Alice and Bob made the measurements, it was an entangled superposition state. Right. This is, one of the strongest arguments that, yes, the world is really quantum mechanical, and, we can't just replace it by something else, by, certainly not by a local hidden variable theory. But then what Wolfram says, and this is in chapter 9 of A New Kind of Science, he just says, well, okay, this is no problem. Just imagine that sometimes there are long range threads between the particles, right? So usually space is local, but when, two particles become entangled, then there's kind of like a thread that allows instantaneous communication between them, right? Problem solved. Right. This is like, the Wolfram method, right? You just, if you can imagine a way that the problem could be solved, then it's solved, right? And so what I spent a lot of my review doing is just explaining, no, sorry, it still doesn't work. It still doesn't give you a picture that's compatible with special relativity. Okay. And so what you can get is that, it's not just a statement about non-locality. It's sort of a statement that, the universe cannot have if the measurements that Alice and Bob are going to make on the entangled particles have not been pre-decided, or sort of were not known in advance, then the outcomes of the measurements on the particles also cannot have been pre-decided. Right? They cannot be explained by hidden variables that go back to the beginning of time. They must be sort of genuine new randomness, right? Or, otherwise you get a violation of locality. Okay, so this is so that was kind of the argument, and like I said, I just made that in 2002. Buried in my review of Wolfram's book. Now that same conclusion, a few years later, became famous when John Conway and Simon Koshin said something very similar in 2006, and they called it the free will theorem. Right. And, the way that they phrased it was that, like, if humans have free will, then subatomic particles must also have free will. and then that, of course, that got all over the popular press. Right. But, I would never have used the term free will here. Right. Because I would say, we could equally well just talk about randomness. Right. And that, but it's sort of I might have called it the freshly generated randomness theory. Okay. And
I see.
it sort of tells you that, no model like Wolfram's from A New Kind of Science can explain, even, existing experiments like the Bell inequality violation, let alone, all the, the experiments of the future. Now, Wolfram never really accepted that. I think most of the community did. He did not, right? But if you look at like what he's done more recently with the Wolfram, I think he called it the Wolfram model of physics. Like what he basically does is he just says, okay, well, wherever we have a result that we can't explain classically, then we'll just graft on the relevant part of quantum mechanics. Right. And it's like, okay, we'll assume that we have a multi-way system, so it can, evolve into superposition. It can evolve multiple ways simultaneously, and that's kind of like quantum mechanics, right? And and also like we will, say, oh, we can derive general relativity, except the derivation will basically be we like crib from a general relativity textbook. We just find out what the Einstein's equations are, and we say, okay, well, whatever is the cellular automaton, it's something that satisfies those equations. Right. So it's like, it's not sort of playing by the rules of physics, right? Where you have to actually, mathematically derive these things, right, from some simple starting postulate. And then ideally, make a novel prediction, right? That's the gold standard. Right. But, so one thing that, when I talked to, Wolfram in person a couple of years ago, when he was in Austin. And one thing that I kept trying to get clarity from him about was, does he predict that scalable quantum computers can work or not? And he wouldn't. He would not give a clear prediction. Basically, that like this multi-way theory, it suggests that maybe quantum computers can't work, but if it turns out that they do work, then the theory can accommodate that also. Right. And so it's kind of, it's sort of parasitic on existing science. It's like, he basically says, just tell me the prediction from existing science, and then I'll find a way to graft it onto this picture.
Have you read any of the papers by Jonathan Garrard?
Yeah, these are exactly the ones that I'm talking about, actually. Yeah. So, I mean, that's maybe there's something there that I'm missing, but, I spent some time on it, and that was the conclusion I came to that, caused me to not spend more time on it.
All right. So before we get to P, no, let's get to P equals at P. Please explain what that is, why P equals 0 is not a valid solution and N equals 1 isn't.
So P and NP are two of the most fundamental complexity classes, which are just classes of problems that are solvable with different kinds of computational resources. So P stands for polynomial time. And it's the class of all of the yes or no problems that a conventional computer, a deterministic digital computer like the one that we're using, could solve using a number of steps that grows like a polynomial function of the number of input bits. Okay, so and that's our sort of rough and ready criterion for when an algorithm is efficient. Right? If it if its running time is scales polynomially with the length of the input. Okay, this is not a perfect criterion because an algorithm that took n to the 10,000 time, right, would be wildly impractical. Okay, but what justifies it is that usually when something is solvable in polynomial time, the polynomial is something like n or n squared or maybe n cubed. Right. Whereas usually when something is not polynomial, you get scaling that looks more like 2 to the n power. Right. That is like exponential in n. And that just, when n is in the hundreds, let's say, then, you can do n squared, you can do n cubed, but 2 to the n is just forget about it. Right. So that's why, like, from the 1960s onward, the polynomial versus exponential distinction kind of became fundamental to complexity theory. And so P is just all of the yes or no problems that are solvable by some algorithm that has polynomial scaling. Okay, so what are some examples of problems in P? Okay, so if I give you a string of text and I ask, is it a palindrome or not? right? Or any kind of basic arithmetic. Most of the things we do with our computers, to be honest, are things that are in P, right? More interesting examples, like given a map, is every city reachable from every other one? Given a graph, is it connected, right? Given
That's P.
That's in P. Given a bunch of boys and girls, and who is willing to date whom, can you pair them off so that everyone is happy with their partner? That's called the matching problem. That's also in P.
And graphics like ray tracing, are you able to say whether that's P?
Yeah, I think the basic problems underlying ray tracing would be in P also. Yes. Now, there are some, and these are all things that, one can learn as an undergraduate in computer science, right? There are, also much more, much more non-trivial examples. Given a number written in binary, is it prime or composite? Okay, that's in P. It was only discovered to be in P 20 years ago. Okay, that's called the Agrawal-Kayal-Saxena, or AKS theorem. Okay, so they gave a breakthrough algorithm. I mean, before that we had known probabilistic algorithms, but they gave the first deterministic polynomial time algorithm for primality testing. If the number is composite, then these fast algorithms do not tell you the factors. Okay, finding the factors seems to be a much, much harder problem, right? Which we can come back to. Okay, but determining primality is in P. Right. Given a bunch of linear constraints, is there a way to satisfy all of them? That's called the linear programming problem. Okay. Again, it's in P, for very non-trivial reasons. Okay. So a lot of interesting things are in P. Okay. But now there's this potentially larger class, which is called NP. Now that does not stand for not polynomial, which some people think. It stands for non-deterministic polynomial time. Okay, so what does that mean? So NP is the class of all the problems where sort of if there is a solution, then you can check the solution in polynomial time. Okay, so if the answer is yes, that there is a solution, then there is some witness, some proof that if it's given to you, then you can check in polynomial time that, yeah, I guess that works. Right. So let's go through some examples. Okay. Solving a jigsaw puzzle. Right. Like imagine a jigsaw puzzle with no picture on it. Right. So you're just trying to fit all the pieces together. Okay. That might be, incredibly cumbersome to do. Right. You might have, exponentially many, possible ways of fitting the pieces together to try. Okay. But if someone has solved the puzzle, then they just have to show it to you. Right. And, you can easily see that, yes, they have solved it. Okay. The famous traveling salesman problem, where, you're given a bunch of cities and you're asked, let's say, is there a route that, visits every city, like with at most 5,000 miles of total travel distance? Right. Again, if there are n cities, there might be n factorial different, routes that you would have to try out. Right. That, with hundreds of cities, that could be massively expensive. But if someone finds a route that works, then they just have to show it to you, and it's easy to check. Okay. So that's also an NP problem. Okay. Factoring. I ask, let's say, does this number have a prime factor that ends with a 3? Or some question like that, right? Where again, the fastest algorithms that we know for factoring take some sort of exponential time. At least the algorithms for classical computers. Okay, they actually take time that's like exponential in the cube root of the number of digits. Okay, that's called the number field sieve. Okay, and that's extremely important for cryptography. Right, because all of the encryption that sort of currently protects the internet, is based on the belief that factoring or a few closely related problems are hard.
Yeah. Even for the factor of 3, isn't there like some algorithm that if you add the digits?
I said a factor ending in a 3.
Oh, sorry.
So,
okay.
I agree. If you just want to know if the number is divisible by 3, that is in P. Yes.
Yeah. Okay.
Yeah.
Okay.
Yeah. In fact, if you want to know if it's divisible by any fixed number, that's in P, right? But if I
Oh,
don't,
cool. Okay.
but if I don't tell you the prime factors and they're like, let's say they're all enormous, and now you have to find them, right? Then that we don't know how to do in P. Okay, but it still is an NP problem, because if someone succeeds in factoring the number, then they just have to show you the prime factors. Right. And at least with a computer, it's easy enough to multiply them. And as I said, it's even easy enough to check that those numbers are prime. Okay. So factoring is another NP problem. Okay. So now the P versus NP question is just the question, well, how do these classes relate to each other? So it's pretty clear that P is contained in NP. Right. So, if you can solve a problem yourself in polynomial time, then you don't even need this witness. Right. You just have the answer to it. Right.
Yeah.
But now the profound question is NP contained in P? Okay. So if I can efficiently recognize the solution to a problem, then does that imply that I can efficiently find the solution? Okay. And so that's the P versus NP question. Okay. And like as soon as you see this question, like some people, like, it takes time to convince them of why it's even a question at all, right? Because they would say, well, obviously not, right? Obviously, there are cases where you're going to need brute force search, and brute force search is going to take exponential time, right? But the trouble is that, as we discussed, like with the example of the matching problem, or the linear programming problem, or the primality problem, right? There are cases where, like, naively, it looks like you have to try exponentially many possibilities. But if you think about it more, then there is a clever shortcut that only takes polynomial time, right? And so what P versus NP is asking is there always a clever shortcut for every problem where we can efficiently recognize a correct answer? And so, that is for half a century, that's been sort of the central unsolved problem of theoretical computer science. And I think it's now recognized as one of the central unsolved problems in all of mathematics.
So, two questions. One, why is this the largest unsolved problem to you? You think this is the greatest unsolved problem in math and potentially even physics? And then number two, this sounds...
So it's not a physics question, right? It's a question. I mean, we could find a related physics question by asking, for example, can the all NP problems be solved in polynomial time by any physical means, right? Which could include a quantum computer, or could even include, a hypothetical quantum gravity computer, or whatever, right? Then we'd be asking a physics question, right? But, P versus NP is a question that can be purely stated mathematically, right? Meaning it has some Platonic answer, right? We just haven't proven what it is.
What I meant was that I heard you say something along the lines of, look, the Clay Institute has many of these problems.
Yes.
And one of the problems is a physics problem, the Yang-Mills problem.
Yeah, well, you could say it's a mathematical physics problem, or it's a math problem that came from physics. Okay, but I mean, the argument that I give is just that if P equaled NP, and furthermore, if the algorithm were really efficient in practice, so not like n to the 10,000, but n squared or n or something, then that would not only let you solve the P versus NP problem, that would let you solve all of the other Clay problems. The Riemann hypothesis, the Yang-Mills problem, right, and all the other ones. And why is that? Because it would mean that we could just ask our computer, right? Say is there a proof of this theorem in this formal language? Like Zermelo-Fraenkel set theory, that is at most, a million symbols long, or at most a billion symbols long. Right. And what it would mean if P equaled NP would be that if such a proof existed, then you could find it using a number of steps that only scaled polynomially with the length of the proof. Right. So like in only polynomially more time than it would take to write down the proof, you could actually find the proof. Right. And so in some sense, mathematical creativity would have been automated.
So a proof of P equals NP would automatically have...
Well, okay. I mean, the caveat is that the algorithm would have to be efficient in practice, right? But the question, like, is there a proof of this theorem in some purely formal language, like first order logic, ZF set theory, right? With at most this number of symbols, that is an NP problem, right? Literally. So that means that if P equaled NP, then it would also be a P problem.
Can you explain what quantum supremacy is?
So quantum supremacy is a term that was coined by the physicist John Preskill in 2012. And it's just referring to sort of the first experiment that you can do with a quantum computer that solves some benchmark problem much faster than we believe that it could be solved with a classical computer. Okay, and notice that I did not say a useful problem. Okay, doesn't have to be useful. Can be a completely artificial benchmark, but it has to be something that is well defined. Okay, so like it can't just be like simulate this physical system with all of its noise, right? You have to give a mathematical specification of what calculation you want, so that same calculation could be done either on a quantum computer or on a classical computer. Okay, and what we want to see is that the quantum computer is faster, not just than classical brute force, but than the fastest classical algorithm that anyone can design. And we want to see that is so for sort of inherent scaling reasons, not just for sort of accidental reasons of hardware, but, the quantum running time is sort of scaling polynomially in a way that the classical runtime is scaling exponentially with the size of the problem. Okay, so that's quantum supremacy. And so Preskill coined this term in order to describe sort of the kind of thing that I and others had been talking about, like in the year or so prior. Right. So my then student, Alex Arkhipov, and I, in 2011, we had a proposal called boson sampling. Okay, which was a proposal for like a very rudimentary kind of quantum computer. That, for example, could be built using photonic components. Okay, so you just generate a bunch of single photons, you send them through a network of beam splitters, and then you measure where they end up. Okay, and that's it. That's all you do here. So we don't think that this is universal for quantum computation, or even universal for classical computation, for that matter, right? It's like, in some ways, it's a very, very limited model of computation. And yet, if you ask, like, okay, what is it doing? Well, it's sampling from a probability distribution, right? Each time you run the experiment, you feed in the photons, they will typically end up in different places, right? Because they sort of move around randomly, and they or rather they evolve in a superposition state. But then when you make a measurement, you collapse the superposition, okay, and you just see one outcome. So you probably never even see the same outcome twice. Sometimes there's 2 photons here, 1 here, 0 here. Sometimes there's 0 here, 0 here, 3 here, and so forth, right? So you see these different distributions. You see these different lists of photon occupation numbers. Numbers of photons in each sort of output port. But then you ask the question. Okay, you could ask, well, what is this useful for? We don't really have a good answer to that. Okay, but then you could ask a different question, which is, how hard would it be for a classical computer to sample from the same probability distribution over photon locations, right? And what we did in 2011 was that we gave pretty strong evidence using complexity theory that problem should be hard for a classical computer. Okay, I could go through, through what the evidence looked like, but basically, if there were a classical algorithm that could sample from exactly the same probability distribution as the sort of ideal version of this photonic experiment, then we say like that would have sort of staggering implications for complexity classes. It wouldn't quite mean that P equaled NP, but it would mean something that's sort of morally almost as bad as that, which is called the collapse of the polynomial hierarchy. Okay, it's sort of like a more abstract version or higher up version of P equaling NP. Okay, and we showed that that would follow if you had a fast, exact classical simulation of boson sampling. Okay, and then if your classical simulation is only approximate, which is sort of the more physically relevant case, because after all, the experiment itself isn't perfect either, right? In the approximate case, we believe that that would collapse the polynomial hierarchy, but there we had to make a yet another conjecture. Okay, and I would say the status of that remains unresolved to this day. Okay, but it's at least seems very plausible that and we showed that here is some well stated problem about a function of matrices called the permanent, and if this problem is sufficiently hard, then boson sampling is hard to simulate using a classical computer, even approximately. Okay, so yeah, so we did that, and then independently from us, there were others like Bremner, Joza, and Shepard who were having related ideas, like about different kinds of rudimentary quantum computers that were not were not obviously useful for anything, but that at least seem to give rise to these probability distributions that are hard to sample using a classical computer for for broadly similar reasons. So one reason why we cared about this was just pure complexity theory, right? It was just pure, can you encode these hard problems into the amplitudes of a quantum computer, right? But then we realized more and more as we worked on it that maybe the experimentalists will care about this, because what we're talking about are devices that seem potentially much, much easier to build than a full error corrected quantum computer, right? Basically, if you could just generate 50 to 100 photons and send them through a beam splitter network and then measure where they end up, that should already be enough to do a boson sampling experiment that is hard for a classical computer, hard for the biggest supercomputers in the world to simulate. Okay, and so then we explicitly talked about that, and then the quantum optics experimentalists got very excited about it, and they decided to start doing it. Initially, like in 2013, it was like with 3 photons, 4 photons. This is all of course trivial for a classical computer to simulate. Right.
Yeah.
The difficulty, ideally, you would expect it to go maybe like 2 to the power of the number of photons. Right. Less than that if there's noise or other things that you can take advantage of. But then what happened was that in 2014, I think Google hired John Martinez, who was maybe the top superconducting qubits experimentalist in the world, and he said, we want to build a 50 to 70 qubit quantum computer, that's programmable using superconducting qubits, and we want to do something cool with it, right? And what is there to do with 50 qubits that's cool, right? Well, there's not a whole lot, unfortunately, right? Most of the actually useful things, they might need hundreds to thousands of qubits, and then crucially, of a much higher quality than Google was, able to make, where you could do like thousands of layers of gates, and they couldn't do that. They can do maybe 20 layers of gates, right? But so what you could do? Well, they realized, okay, we can do some version of boson sampling, right? Except except now more adapted to their hardware. So we talked to them about that, and we said, yeah, that sounds reasonable, but we're going to we then had to adapt the theory from boson sampling to superconducting qubits, to the kind of thing that they were building. So we did that like 2016, 2017. And then in 2019, Google announced that they had actually done this. So they had built a 53 qubit device called Sycamore, and they used it to sample from some probability distribution over 53 bit strings. That you get by just applying like a random sequence of quantum operations to these qubits. And then, at first they were saying, well, with the best classical algorithm that we can think of, it would take 10,000 years to do the same thing on a supercomputer, right? And the press loved that, right? And they ran with that number, and that turned out to be wildly over optimistic. Okay?
Right.
So
I could imagine Michio Kaku would love that.
Yes. Oh, I'm sure he would. Right. But the hard part in quantum computing, if you want to be intellectually honest about it, is that you always have to compare against what is the best thing that anyone could do with a classical computer. Right. And you're only winning if you do better than that. Okay. And what's the best thing that you can do with a classical computer is often far from obvious. I mean, after all, that's what the P versus NP question is about. Right. So indeed, what happened over the next couple of years is that people got better and better at simulating the Google type of experiment with classical computers by, taking advantage of the noise and taking advantage of the fact that each qubit can only sort of talk to its nearest neighbors. So you can sort of take advantage of all the current technological limitations of Google's experiment in order to simulate it faster with a classical computer. And I would say that the current situation is that the Google chip, is still somewhat better than any classical solution that we have for the task of simulating itself. Okay. Like if you measure, let's say, by the total energy cost, right? Or by, the money that it takes to run it, or the CO2 that's emitted.
By steps?
But well, by the trouble with steps is that, you like with a classically, you can always roughly have the number of steps by just using twice as many cores. Okay. So these problems are very, very parallelizable. Right. So, you can always do it faster if you're willing to go to AWS or whatever and just say, I want, this massive number of cores. Right. But then, it's interesting. Right. But then at some point, for the comparison to be fair, you should maybe be talking about money, or you should be talking about, the energy, the electricity that gets spent, or, and if you look at metrics like that, then I think that the quantum computer, still wins on some tasks, but only by a couple orders of magnitude at this point.
That sounds a bit human, though, because if we're measuring it by money, firstly, that's human. But if we're measuring it by energy, isn't it then not based on the algorithm, but based on our current cores, and maybe in the future Apple comes out with M5?
Of course it is. Of course it is. So you could say that, you are fighting against a moving target, right? Like quantum supremacy could be achieved and then unachieved because, the classical hardware and software, right, will both get better. And so if you want to claim that a quantum computer is better for something, right, then, you may have to keep improving the quantum computer, just for that statement to still be true. Okay. Now the hope, let's be clear. Okay. The hope is that eventually you have an error corrected, programmable quantum computer. And at that point, you can scale up to as many operations as you want on as many qubits as you want. Okay. And at that point, you could use like millions of qubits to factor some enormous number, right? That unless there's a breakthrough in classical algorithms, that just cannot be done classically within the whole lifetime of the universe. Right. Mm-hmm. So that's the eventual goal. Okay. But we're not there yet. Okay. And with these, what we can do today are these sorts of sampling experiments, right? Where, we're solving problems that don't have a single right answer, right? We're sampling from a distribution over possible answers. And a key drawback of these problems is that even just to verify what the quantum computer is doing already appears to take exponential time with a classical computer. Okay, which means that we're sort of inherently limited in how far we can scale this. If you scaled it to 300 qubits, even if it worked, how would you ever prove it? Right? How would you ever convince a skeptic of what you had done? So we're sort of forced to stay in this regime where the advantages that we can get over classical computers are relatively marginal ones. Okay. But at least we can now do that, right? 5 years ago, we could not even do that. Okay. And now we can, right? And that's I think it's a step forward. I think it's taught the experimentalists a lot about how to actually integrate, large numbers of qubits. And, and maybe scientifically, the most important thing that they learned from these quantum supremacy experiments was that, like, the total amount of signal you get, what's called the circuit fidelity, it's falling off exponentially with the number of operations, which sounds kind of bad, right? But the good news is that it's merely falling off exponentially and not faster than that. Okay, so basically the total fidelity, like let's say, each individual 2-qubit operation has a fidelity in Google's experiment of about 99.5%, right? And there's about 1,000 such operations. Okay, and so then the total fidelity that you get for the circuit, it looks like just 0.995 to the power of 1,000, right? Which is like the simplest prediction that you could possibly make. And as long as that remains true, then ultimately quantum error correction should work. Okay, so the people who believe that scalable quantum computers are impossible, such as Gil Kalai is a famous one, right? What they basically have to believe is that either quantum mechanics itself is going to break, which let's face it, that would be far more exciting than a mere success in building a quantum computer.
Sure,
right? That would be a revolution in physics. Or else they have to believe that there's some sort of conspiratorially correlated errors that will violate all the assumptions of the theory of quantum error correction. Okay, but from the quantum supremacy experiments, we can now say we see no sign of those conspiratorially correlated errors.
And you're referring to superdeterminism?
No, I'm not. I mean, superdeterminism is like so bizarre that like it's not even clear that would have any empirical consequences at all. Right? Because that's just saying there's a giant cosmic conspiracy theory that just predetermined everything that would happen from the beginning of time. Right? It was like you can always believe that, but it's sort of explanatorily worthless. Right? It doesn't, it has no power to explain anything. Okay, so the more interesting thing, if there were these conspiracies in the errors affecting qubits, that would be something that would be empirically observable, right? And if the correlations were strong enough, then conceivably that could even kill quantum computation. Okay, but there are some basic difficulties here. One is that it's very, very hard to design a model of correlated errors that only kills quantum computation and that wouldn't also kill classical computation. Right? If you kill classical computation, then you've proved too much because we know that scalable classical computers can be built. Right? So okay, but then the other thing you can say is that from the quantum supremacy experiments, we see no sign of these correlated errors. The errors look pretty independent, and in that case, it's as long as that remains true, then it's just a quantitative question. You just have to get the accuracy of each operation to be high enough, like instead of 0.995, maybe 0.9999, right? And then at that point, quantum error correction should work.
Now, we both got to get going shortly, and I wanted to end on the topic of consciousness. So why don't you talk about your critiques for IIT, and then also what the pretty hard problem of consciousness is. But before you do that, I just wanted to ask you a yes or no question about if you saw Tim Palmer's response to your critiques on superdeterminism in his recent article. Tim Palmer's article on superdeterminism without conspiracy is listed in the description, and you should know that Tim Palmer was on the Theories of Everything podcast, and that link is also in the description. He was on with Tim Maudlin at the same time, talking about the interpretations of quantum mechanics.
Yeah, I mean, I think it is a conspiracy. I mean, I think that he redefines terms in an utterly perverse way in order to make it look like it's not one. But I don't think that you actually explain anything new that you couldn't have explained without this. And there's it's a problem because I only have so much time in life to spend. You're right, and like you've asked a lot about Wolfram's ideas, about Tim Palmer's ideas, right? But like there are so many ideas out there that seem like orders of magnitude more plausible to me than these, right? These are just these people have succeeded at like getting out to the public, right, and putting their message before the public. But like scientifically, I regard these as worthless ideas. Okay. So, um, okay. Yeah. But now, consciousness. Yeah.
Yeah.
So integrated information theory is another thing that I think has, okay, maybe like it was worth trying, it was worth thinking about, but that has also become, a worthless idea, a pathological idea. Okay. So it's a proposed, theory of consciousness, or at least of what things are conscious and what things are not, that was originated by Giulio Tononi. Okay, and also pursued by a bunch of other people such as Christoph Koch. I think Max Tegmark was into it, and basically what it says is that there was some, you could take any complex system, and then there was some quantitative measure that that you can calculate for that system that somehow measures how interconnected all of its components are, right? And they call that phi, right? And the larger is that phi measure, the more conscious the system is. Right. Now, you could say, what is this phi? Right. Well, the actual definition of it keeps changing. Right. So, there's not actually the one fixed thing that you can critique.
Uh-huh.
Right. They keep fiddling with it, with the definition of it. And they said, and if you read the papers about it, like what they say is, well, we have these axioms of conscious experience, and then, we derive phi from these axioms, but actually there's no derivation at all, right? It's sort of like pseudo mathematics. It's like, they state the axioms, and then at some point phi just appears. It just shows up,
Right.
not having been derived in any way, right?
So they show it's consistent with the axioms, but not derivable from them.
Yeah. The axioms are not even clear enough to me for me to really understand what they are saying. Right.
Okay.
But at least the phi measure, at least like that seems reasonably clear. Like once you've decided what are the subsystems, what does it mean for a subsystems to be connected to each other and so forth, then, and you decided which version of phi you're working with, then, you can actually calculate these numbers. Okay. And then, their case, they were neuroscientists, and they said, well, there seems to be much higher connectivity in the cerebrum than in the cerebellum, for example, right? And the cerebrum is associated with consciousness, and the cerebellum is not, right? Mm-hmm. So that was the kind of evidence that they gave. Okay, but then I wrote a blog post about this like 9 years ago, where I pointed out that we could easily invent systems that have massively higher phi than the human cerebrum, right? But that are just like a gigantic grid of XOR gates or something like that, right?
Without processing?
Yeah. Well, okay. Yeah. Maybe, they do process something, like they compute the XOR of a bunch of bits, right? But it's all like completely regular. It's like there's not even anything interesting or intelligent going on there, let alone anything conscious, right? And yet, if you calculate this number that they put forward, then you'll get that the connectivity between the different components, can be arbitrarily large, right? Just depending on how big you make the thing, right? You could make it, and I said, and to me, that seems like a reductio ad absurdum. Right. It seems like, okay, the theory is just making a, like an utterly wrong or absurd prediction. And therefore, this connectivity, it might be correlated with consciousness in various cases, but it cannot be identical with consciousness, right? Because we can make it, huge in systems that are obviously not conscious. Okay. And so then Tononi's response to me was extremely interesting. Okay, because what I say, like, the way I put it was like, he didn't just bite the bullet. He like basically devoured a bullet hoagie with mustard, right? He said, look, the problem is that you're just, using your intuition, but you have to rely on the theory. And what the theory tells you is that this giant grid of XOR gates is conscious. In fact, it's much more conscious than you are, right? And you have to be bold and just believe what the theory says. And, and my response at that point was like, okay, if a theory is sort of getting right, the things that the cases where we already thought we knew the answers, right? Then you might be interested in what does the theory say about the really hard cases, like let's say about a fetus or about a coma patient or about an earthworm or about an AI program, right? But if the your measure of consciousness is already telling you that a potato chip bag is conscious, right? Or that any old sort of uninteresting physical system is conscious just because of this sort of these sort of mundane properties that it has, right? Then okay, if it's gotten that wrong, then sort of what is there for it to get right? Right.
Yes.
Right. It's like how else would we validate the theory in the first place, except by seeing that it at least gives the right answers in the cases where we already thought that we understood what we meant by consciousness and so forth. So that was kind of the point where I got off the train, and and this theory has just continued, generating, I don't know, hundreds or thousands of publications over the last decade. I saw that there was a letter recently by like a bunch of philosophers and neuroscientists who said that, integrated information theory is pseudoscience. Right. And then there was a response, and there was, I didn't even wade into this because I felt like I had said my piece, a decade ago.
Yeah.
Right. Well, it's like, these are ideas that are worth exploring. But then once you get, once you see that you make a prediction that's badly wrong, then I think you have to go back to the drawing board. You have to say, okay, well then, this is not a measure of consciousness, right? And instead, they just keep trying to, rescue the theory, and at some point, that kind of thing does degenerate into pseudoscience.
So it sounds like what he's saying is that what you think of as a reductio ad absurdum is actually a productio ad correctum. You're proving something correct, and we should listen to the theory.
Yeah.
So why can't we follow that same logic when it comes to the many worlds and say, look, on one hand, some people can say it's a reductio ad absurdum. You're predicting all of these other worlds.
Yeah.
But then Sean Carroll may say, no, we should be listening to
the theory. Well, I would say that the difference is that quantum mechanics gets, every single case that we can check, it gets the right answer.
Right.
Right. That's been true for 100 years. There are zero counterexamples. Right. And that's now even with very, very complicated entangled quantum systems. And so then, it is natural to just want to do the extrapolation and say, assume that this continues to be true up to arbitrary scales. Then what does that mean? Because we've seen no sign otherwise. Right.
Yeah.
But like with consciousness, like I feel like if you want to decide what is or isn't conscious, we have to start with definitions, right? Like, what do we even mean by consciousness? Well, like it is, whatever it is, like it is some sort of thing that we regard ourselves as having, and that we regard this glasses cloth here as not having,
or at least not having anywhere near as much.
Right. Yes, exactly. It's not having nearly as much. If you say that this glasses cloth has much more consciousness than I do, then I say, well, what do you even mean anymore by the word consciousness? Right. I don't think you're talking about the same thing that I was trying to talk about.
Right. Yeah. Okay. And then the pretty hard problem of consciousness is
that's just the problem of So the hard problem of consciousness, as articulated by the philosopher David Chalmers in the 90s, is to explain why there is ever anything that it is like to be. Explain how subjective experience can arise out of mere matter or mere physical systems obeying the laws of physics. And in some sense, this is a problem that goes all the way back to Democritus in like 400 BC.
And you have a book on this.
I do. Yeah. I mean, Democritus already stated this problem in a remarkably modern way. Right. And, and certainly Descartes, asked this question centuries ago. So this is, one of the great problems of philosophy, or maybe, the great problems of all of human existence. Right. And it's not even clear what an answer would look like. Or what kind of thing could be an answer, let alone how to find that answer. Okay. But so then, He said, whenever you encounter something that is just way too hard, whether it's the hard problem of consciousness or whether it's P versus NP, right? Then, it's natural to want to scale back and say, well, is there an easier related problem that we can make progress on? Right. And so what I called the pretty hard problem is just the question, which physical systems are associated with consciousness and which are not. Right. Mm-hmm, and so, you could imagine answering that without having to answer among the ones that are conscious, why are they conscious or how? Right. You could imagine just giving a criterion that agrees with intuition in all the cases, that we can think of, and that, and that actually calculates, some measure of consciousness, from some simple starting point. That is precisely what IIT was trying to do. And I respect that it was trying to do that. I just don't think that it succeeds.
Mm-hmm. Well, Professor, thank you for spending so long with me.
Sure.
It was so much fun.
Yeah, all right.
I hope to speak with you again.
Yeah, all right. Take care. Talk to you later.
Bye-bye. If you enjoyed this podcast, then one that I recommend is the one with Tim Palmer and Tim Maudlin, as they're both superlative explicators of quantum theory, and superdeterminism was a central tenet of that conversation. The link is in the description. Also, if you'd like to donate, as we've had trouble monetizing the channel with sponsorship, then please do so at patreon.com/KurtJaimungal, or the PayPal link is in the description, as well as a crypto link. Your support helps TOE delve this much in depth with each episode, keeping it high quality, and helps us continue. Thank you so much. Every dollar helps. The podcast is now concluded. Thank you for watching. If you haven't subscribed or clicked that like button, now would be a great time to do so, as each subscribe and like helps YouTube push this content to more people. You should also know that there's a remarkably active Discord and subreddit for Theories of Everything, where people explicate TOEs, disagree respectfully about theories, and build as a community our own TOEs. Links to both are in the description. Also, I recently found out that external links count plenty toward the algorithm, which means that when you share on Twitter, on Facebook, on Reddit, etc., it shows YouTube that people are talking about this outside of YouTube, which in turn greatly aids the distribution on YouTube as well. Last but not least, you should know that this podcast is on iTunes, it's on Spotify, it's on every one of the audio platforms. Just type in Theories of Everything and you'll find it. Often I gain from rewatching lectures and podcasts, and I read that in the comments, hey, TOE listeners also gain from replaying. So how about instead re-listening on those platforms? iTunes, Spotify, Google Podcasts, whichever podcast catcher you use. If you'd like to support more conversations like this, then do consider visiting patreon.com/KurtJaimungal and donating with whatever you like. Again, it's support from the sponsors and you that allow me to work on TOE full-time. You get early access to ad-free audio episodes there as well. For instance, this episode was released a few days earlier. Every dollar helps far more than you think. Either way, your viewership is generosity enough.